All right, so welcome back to class. Yesterday, we were talking about surfactants. So, one thing really important to know for your lab this week, lab number 6, and your final exam, is that surfactants are chemicals that lower the surface tension between two liquids. So when they lower the surface tension, they allow solutions that shouldn't mix, like oil and water, to actually mix. Then we looked at 4 types of surfactants yesterday, and now today we'll look at kind of what this means in the petroleum industry. So, in oil field emulsions, which is a very common occurrence, one of the liquids is aqueous and the other is crude oil. That aqueous liquid is typically water or salt water. The amount of water that emulsifies with crude oil is different all over the world. It could be less than 1% or sometimes even bigger than 80%. So, depending on where your oil comes from, offshore, or it could be like the tar sands in Canada, could be from fracking. Depending on where you get that oil from, there could be little to no water or lots and lots of water. And remember what I mentioned about water the other day? Water is bad. Water can cause corrosion, so it's not ideal. Crude oil emulsions form, of course, when water and oil mix. They come into contact with each other, but there has to be sufficient mixing. And typically, there's an emulsifying agent or emulsifier present. The amount of mixing that's allowed and the presence of an emulsifier are very, very important for the formation of an emulsion. So how does it happen? Where does mixing, for example, happen in the petroleum industry? Well, the mixing is often referred to as the amount of shear, and it can happen at a few points. It can happen as oil flows through reservoir rock, down underground. It can happen through perforations, so small holes or pumps. It can happen when it's flowing through tubing or lines. Okay, so this is pretty common in the petroleum industry. When it's going through valves, fittings, and chokes, surface equipment, or even when there's gas bubbles released because of a phase change, these gas bubbles can help mix the solution and cause it to form an emulsion. So basically, anywhere where the liquid is getting bumped around, it's going through a small hole, it's getting forced into a space, you would notice that the oil and water would be mixing, forming an emulsion. So in the petroleum industry, we don't want this to happen. We don't want water to be mixed with the oil. So they use emulsion breakers. These are special chemicals used to separate emulsions, for example, oil and water. They're commonly used in crude oil processing, um, where we get rid of that salt water. Whoops. Yeah, so like I said, in the petroleum industry, we do not want these emulsions to happen. We do not want salt water in the oil. So there's commonly a way to separate them using different chemicals. Remember how we can separate emulsions? We can use, sorry, not we can use, but we learned that the way to separate an emulsion is to get the dispersed medium or the dispersed chemical to aggregate, join together, or group together so it separates out. So this is an example. Obviously, you do not need to memorize this, but this is an example using electrochemistry. This is an electrode configuration where they use electrochemistry or electricity, really, to separate the polar water molecules from the oil. big thing and something I will probably ask you about on, say, like the final exam is, like, why do we want to separate the water from the oil? Well, it's all about corrosion. Salt or saline water can cause major, major corrosion problems. So yeah, this is an example on the, sorry, on the right here, using electrochemistry, using electrodes to attract the polar water. The water goes out one way and the oil goes out the other, but you don't need to memorize that or memorize this for the final or anything like that. All right, so the finale, the last section of chapter 5. Chapter 6, like I said, is very, very short. So we'll start that tomorrow, which is perfect because that'll get us ready for the lab next week. Chapter 5 is about corrosion or chemical corrosion inhibitors. So just give me 1 second and we'll start this. All right, so chemical corrosion inhibitors. Now, actually, this slide 119, I took directly from Chemistry 1121. So now I know you guys didn't have me for 1121, but we all pretty much teach the same thing. Uh, this is something you learned back at the end. Yeah, around the end of Chemistry 1121 when you were doing electrochemistry. So corrosion. Corrosion is, of course, a natural process. It happens naturally, and it converts a refined metal into something more, actually more chemically stable, like an oxide, hydroxide, or sulfide. The rust you typically see in real life with metal is oxide, so iron 2 or iron 3 oxide. Corrosion is basically the gradual destruction, so over time, very slow destruction of metals by chemical and electrochemical reactions with their environment. Now, how does it happen? Well, dissimilar metals have different electrode potentials. And you can remember back in chemistry 1120, these different electrode potentials can result in a redox reaction. So when two or more come into contact with an electrolyte, so like salt water, for example, one metal acts as an anode, the other acts as a cathode, and we see a redox reaction happen. Electrolyte being typically salt water. If the electrolyte contains only metal ions that are not easily reduced, the cathode in the reaction is the reduction of dissolved H to H2 or O2 to OH. So this is typically a metal ion that is in the electrolyte for corrosion. So this is an image I took from Chemistry 1121. So, again, I know you guys didn't have me, but maybe your last instructor, Gabby or Michelle or somebody showed you this. If not, this is, again, a slide from Chemistry 1121. This is the rusting or corrosion of iron in the presence of oxygen, and typically water helps this happen because of the sodium or salt ions that are in there. Now, obviously, this is from Chemistry 1121. So you don't need to memorize this, don't worry. But this is just a reminder of the rusting process. What we're more concerned with is what does corrosion mean in the petroleum industry? So we're going to look at sour, sweet, and oxygen and bacterial corrosion. Then we'll look at corrosion inhibitors, and then we are finally done chapter 5. So there are 4 types of corrosion that we're going to look at today. The first is sour corrosion. Sour corrosion is the degradation or breaking down, like rust formation, of a metal surface due to the presence of a highly acidic, and that's where the word sour comes from, environment containing hydrogen sulfide. Sour corrosion can cause metals to fail at stress levels higher than normal. So sour corrosion is corrosion, the breakdown of metal in highly acidic environments. Typically, sour corrosion is containing hydrogen sulfide. Sour corrosion is very common in the petroleum industry because hydrogen sulfide is a very common byproduct of oil refining. Sour corrosion can happen in like storage tanks or pipelines. Basically anywhere where hydrogen sulfide is built up on metallic surfaces. When you see the hydrogen sulfide being in large amounts or in high concentrations, the metal can become embrittled or weak due to the contact with hydrogen sulfide, and this causes corrosion. So basically all you need to know here is sour corrosion is when metals corrode because of hydrogen sulfide, acidic hydrogen sulfide. Sweet corrosion is corrosion that happens when you do not have high levels of hydrogen sulfide. It's other chemicals that are causing this corrosion. Carbon dioxide, carbonic acid are usually what cause sweet corrosion. This is interesting. Sweet corrosion is a term normally used in oil industries to differentiate, like to tell the difference between corrosion that's caused by, high hydrogen sulfide or high sulfide fossil fuels, and fossil fuels that do not have high amounts of hydrogen sulfide. So you would hear the word sweet as kind of like an opposite to sour, meaning, there's not a lot of sulfides present in this gas, so it's corroding because of other reasons. Carbon dioxide is acidic, so is carbonic acid. Carbonic acid is typically formed when carbon dioxide is dissolved in water. So sweet corrosion is still related to acids, but it's not sulfide related. So sour is related to sulfides, sweet is still acidic, but not related to sulfides at all. Now, hydrogen sulfide, big trouble. Sweet corrosion is usually less aggressive than sour corrosion. Sweet corrosion is definitely a major concern, like definitely an issue because of pitting. Pitting is, so say you had like a metal surface. Pitting is when you get like little small type I was gonna say small rusting, but like basically it's corroding in a way where you get like these little pits. And I don't know if you guys are familiar with the word pit, but a pit is like a small hole. Pitting can happen with any metal. I see it back home in my car all the time. Kind of like Qatar, back where I live, it's next to the ocean. So anywhere next to the ocean, you obviously have lots of salt water. And in the winter where I live, when it's snowing, they put salt on the roads to prevent ice from forming. So like basically my car back home, uh, it's in a very high salt environment. There's salt in the air because I live next to the ocean. And then there's salt on the roads in the winter because it helps the ice melt. And the salt can cause pitting in the paint and metal on my car. So you'll see sometimes in an older car these little divots or little holes in the paint, which is typically fine if you take care of them. If you don't take care of them, it can ultimately result in larger holes. The pitting will typically grow and grow until you get something happen like a material failure. So a pipeline breaks or something. All right. So anyways, sour, basically all you need to know there is sour corrosion, hydrogen sulfide, sweet corrosion, still acidic, but not hydrogen sulfide. It's typically carbonic acid or carbon dioxide. These, again, are basically the same thing. Carbonic acid is when you take carbon dioxide and you mix it in water. Carbonic acid is one of the reasons why, like Pepsi is bad for, or Coke are bad for your teeth because they're so acidic. Okay, two more. Oxygen corrosion. Well, this is the easiest definition. Oxygen corrosion is corrosion that happens in the presence of oxygen. It's related to oxidation. So just like an apple or banana or avocado turning brown in oxygen, metals can do the same in the presence of oxygen. Now that might seem simple, or that might seem common sense, everything is in the presence of oxygen, but not necessarily. Deep underground where you're drilling for oil in a very tight oil well, there might not be as much oxygen, for example, as up on the surface. So oxygen corrosion happens when you have high levels of oxygen. The presence of significant quantities of oxygen, and of course you need water and electrolytes, again, typically salt, can cause dramatic corrosion. This is your classic corrosion. So this is like the corrosion that you would see, on a car, and somebody left a car out in the desert, or back in Canada, you would see this a lot. This is like I said, your classic form of corrosion. It just happens naturally in an oxygen-rich environment. A good example of oxygen corrosion, actually, my friend works on a boat. So he works for Marine Atlantic, which is a boat company, and these guys deliver supplies to the oil rigs in the Atlantic Ocean. And he's a little higher up now, like his job is a little more important. But when he first started, his whole job was coating or painting surfaces to prevent them from rusting, because he worked in the ocean. So the ocean, very obviously a salty environment. So with all the oxygen, the salt, the water, boats are made of metal and very, very susceptible to corrosion. So his job mostly was coating or sorry, painting that boat over and over again to prevent rust. There's a message in the chat there from Saif. If you keep your car outside, how come corrosion doesn't happen? And it's actually because of this. Your cars, your vehicles, are coated in paint or other chemicals to prevent them from rusting. And again, this is kind of what happens back with my car in Canada. If there's like a chip in your paint, if somebody scratches your car, or maybe you have a small accident and the paint gets removed, you will notice it will rust very, very quick. So the question, how come if your cars are left outside, why aren't they big buckets of rust? It's because the metals of your car are coated in something. Now, I don't know much about cars, but if it's typically paint to help it stop rusting. Yeah. So what painting does is it reduces the metal's surface exposure to oxygen. If you paint a metal or coat a metal, another term you guys learned in chemistry 1121 is galvanized. So you can help coat the metal using an electrochemical reaction. But anytime you coat or cover the metal, you're preventing oxygen from getting in contact with it, which means you will reduce rust. The last and final type of corrosion is bacterial. This is corrosion where bacteria, so living organisms, can help or can cause corrosion. This is definitely not something that we deal with too much in chemistry. This is more a biology example. Um, but bacterial corrosion can happen on any type of material, metal or non-metal. So bacterial corrosion does not require oxygen. This is about the only thing you would need to know about bacterial corrosion. So um, I'll give you a summary of the four of these in a minute. But in a humid environment where even if there's no oxygen, bacterial corrosion can happen, and it can cause pitting, holes, or spots in your metal. And this could happen in the pipelines in your oil and gas industry. There are bacteria in your oil wells. So bacterial corrosion can happen underground in pipelines, even if there's no oxygen. So let me give you a summary of the four types of corrosion. There's sour corrosion. That's corrosion in the presence of hydrogen sulfide. There's sweet corrosion, still an acidic type of corrosion, but it's typically carbon dioxide or carbonic acid. There's oxygen corrosion. That's your normal type of corrosion where things just corrode in the presence of oxygen. And then there's bacterial corrosion, which can happen on metals and nonmetals, and it does not need oxygen to happen. Bacterial corrosion can take place anywhere, anytime. So 3 slides left and we are done chapter 5. To prevent this from happening, I obviously mentioned you could paint something, but it's kind of impractical to consider painting like a pipeline. You wouldn't paint, a kilometer-long pipeline on the inside to prevent corrosion. So what we can use in the oil and gas industry is a chemical inhibitor. Or sorry, a corrosion inhibitor, not a chemical inhibitor, a corrosion inhibitor. This is a chemical compound that you can add to your oil or gas to decrease the rate of corrosion. The nature of a corrosive inhibitor depends on what you're protecting. So like, is it metal? Is it plastic? What type of chemical are you protecting? Typically in the oil and gas industry, it's metal. And two, what are you trying to cancel? Like, think about sweet or sour corrosion. This is corrosion that's happening in an acidic environment. So if you wanted to stop, for example, sour corrosion, you could neutralize or cancel the hydrogen sulfide acid by adding a base, typically a weak base. So the corrosive inhibitor that you add depends on what you're trying to protect, whether it's metal, plastic, is it stainless steel, is it pure iron, and then what type of corrosion are you trying to stop? The corrosive agents are generally oxygen, hydrogen sulfide. So this is oxygen corrosion, sour corrosion, sweet corrosion. And a really easy way to remove oxygen is to add nitrogen compounds like amines or hydrazines. Amines or hydrazines will turn the oxygen compound into water. So when I've asked this before on a test, wink, wink, well, no, sorry, you guys, you're not going to have a test, obviously. You'll have your final exam. But when I've asked this before on the final, wink, wink, if I ask you what's a good example of a corrosion inhibitor, it's nitrogen-based compounds. Amines, so again, nitrogen, are used in boilers to minimize the effects of acids. Amines, guys, are typically weak bases, And you guys learned in chemistry 1121, when an acid and base interact, they neutralize each other. So volatile reactive amines are used in boilers to minimize the effects of acids. Amines can also help perform a protective film on the steel's surface and stop corrosion from happening. It can inhibit. Inhibit, guys, just means stop or slow down anode or cathode reactions. In oil refineries, hydrogen sulfide can corrode steels, so it's often removed using amines. Again, nitrogen-based compounds. What an amine would do is convert hydrogen sulfide to a different sulfide molecule called a polysulfide. You don't need to know that, but the key thing here is wink, wink, wink. If I asked you what kind of chemicals they add to oil and gas to stop corrosion, it would be nitrogen-based compounds. And it's good to know that nitrogen-based compounds are weak bases. Okay, so yeah, that's basically it for today. That's the end of this chapter. Chapter 5 is finished. This means we have 4 classes left. We have class tomorrow, and then we have 3 classes next week, which means I can hopefully, well, I shouldn't say hopefully, I know we can finish chapter 6 next week. Probably chapter 6 should only take me maybe 2 classes, maybe 3, and then we can do review for your final exam in the last class or 2. So yeah, that's it for me today. If you guys have any questions, let me know. If you don't have any questions, I will, of course, see you in class tomorrow. Don't forget, you have lab number 6 due this week. Make sure you get that done. I think it's due next Monday. And then on Tuesday next week, we'll do our last and final lab. So yeah, if you have any questions, let me know.